Sound check. Oh.
The slides. I think you asked for next slides unless you want to use it remotely. Just say next. Yeah.
Well, that's a bit of an unusual fault.
So the meeting
I don't
has
think I've seen that particular failure mode before.
Okay, just looking at the slide deck now. Oh, it's fine. It's just difficult to read the first slide. That's all. So for anybody who's getting themselves into this room, this is Tsvwg. Our wonderful first slide renders quite well in the proceedings and pretty awfully here. So I'm This is a non-critical problem. We're about to start the meeting, so we're just gathering people. If you are one of the presenters and you want to do a quick sound check, please do. We will start in just a few minutes. David, Wes, can you do a quick sound check, please?
Yep, can you hear me?
Yeah, Wes, good morning.
Good morning.
And can you hear me?
Excellent,
Yes,
I can hear you, David.
Okay, excellent.
Can you hear me?
We can hear. Thank you, Tom. Right, okay. I suggest we start the meeting. So welcome everybody. This is Tsvwg. It's the Transport and Services Working Group. We have a 2-hour agenda for today. I'm Gori Fairhurst. I'm one of the co-chairs. I'm the chair who will be on the platform. Remotely, we have Wes Eddy and David Black. Apologies for the first slide. It's quite cute, but it's not very informative. The rest of the slides, I'm sure, will be readable. So maybe I fibbed. This is the note well. The note well is traditionally in small print. If you haven't read the note well by now, then you really should. IETF note wells apply to all IETF contributions on the mailing list, at the microphone, and via any other means, and are the ways in which we ensure that we have dealt appropriately with IPR and other issues that relate to the IETF process. We're using MeetEcho for this meeting, which means that the mic queue will be via MeetEcho. If you're going to the mic, please state your name. It's important that people can hear your name in the proceedings in the audio, so please make sure you do say your name as well as raising your hand in Meet Echo. If there is anyone who hasn't yet joined the room using the QR code or by launching the Meet Echo tool, please make sure you do this. This is also important for the IETF proceedings that everybody in the room has joined the meeting in some way. If you're frightened about joining and staying joined, you can join just for a moment so that we tag you as being part of this group and we can see that you're a participant. So please join online and register for the blue sheet. This is the Tsvwg status slide. There are 5 internet drafts with the working group chairs and authors, all past working group last call in different states of completion. The ECN and CAPS for lower layers draft is shepherded by David Black and needs text to replace the reframing interaction words in that document. This is a small change, but it's a change that has to be agreed with the authors and will be put on list once that change is complete. ECN for tunnels that use shim headers has a similar issue that has been resolved. Both of these documents are ready for working group shepherd write-up, and the changes will be posted to the list during that process, and then it will be passed upwards to our AD. We plan to do this before the next IETF. We have 3 drafts that have completed working group last call some time ago and have gone through an extended process of further review and shepherd write-up to document the process. These are L4S architecture, L4S identifier, and L4S AQM. We plan to issue that shepherd write-up soon, and Wes might wish to comment at this moment if there is anything else to say. Wes, is there anything else to say about these?
No changes since we talked about it earlier this week. I think everything you said is accurate, Gory.
Good. Right, we don't need to review these things, and we will move straight to the agenda for Friday then. Friday's agenda looks like this. We have transport protocols for DCCP. We have a differentiated services section where we're going to look at NQB and DSCP considerations. And we have transport for UDP, where we're going to look at the UDP options work. We don't anticipate any other business, but now is the opportunity if you'd wish to hack or modify or make suggestions on our agenda. Does anyone have any agenda suggestions that we should take into consideration? In that case, that's the agenda for this meeting, and we will proceed with the announcements. I think there is one announcement, and it ain't here. I will speak to that. We'll cover that after Marcus's talk then. That's fine. So Marcus, you're up for the DCCP slides. Shh. Hey, wait a minute. Wes, can you advance these slides if I launch them, or do you have to launch them? Or David, or whoever.
Yeah, I don't know.
Okay.
Doesn't look like that.
How about you, one of you two launches this slide deck? And this is Marcus, and we'll get your slides up in just a second.
Okay, can I start?
You can start, your slides will appear shortly.
Yeah, good morning, everybody. Markus Amann from Deutsche Telekom. I'm here as a 5G ATSS enthusiast, but more important, I think, on behalf of the MP-DCCP draft authors group. So let's see if the first slide comes up.
If not, then I can launch them from here. I'll launch them from here. There you go.
Yeah, so I want to give some insights into our progress on the multipass DCCP draft, and yeah, the main changes which have happened since last IETF are around the handshaking procedure. Sorry, it's the old slide set, it's not the last one.
Yeah, well, the problem is we don't have, the new slides are not in MeTecho, and I don't know how to get them. And that's true, there's a lot of missing slides.
Okay, shall I go forward with them?
You have to for now. Next slide.
Yeah.
No. Then I will take this one. Unfortunately, that is the old version of the slide set. So if you want to have the latest one, please look into the agenda. There you will get it. Yeah, we have changes, or we have a lot of changes in the draft since last IETF. So we finalized the handshaking procedure. I have some more information about that in one of the next slides. We did a lot of changes in the MP Prio option. Also here, I will give some more information about it. MP Prio is used for fine granular path management, to enable, disable paths, to set a path into a backup mode so that it is only used if no other path is available. And we can also use it for path prioritization as an input for scheduling decisions. Maximum packet size, I think, is also an important topic. That is something what is already considered in the DCCP RFC 4340, where the maximum packet size is described how it can be detected and how it can be communicated to the upper layers, to the applications itself. And we consider now in our draft how this has to be treated in the multipass context. So we defined, I think, a nice strategy here to deal with that and to keep compatibility with a single pass DCCP. We started to define some closing procedure, defining two new options, MP close and MP fast close. I will also have separate slides on this. We added a congestion control sections or congestion considerations for bottleneck fairness with single pass. Yeah, I think that's also worth to read. I do not have additional slides here. In general, we maintain the draft at GitHub, so you will find much more information. You will also find the individual pull requests there, which describe exactly what we have done. Along with the draft development, we also developed our open source code at GitHub, where we have a Linux reference implementation for multipass DCCP available, and that one we extended with some of the changes we made in version 2 and 3 of the MP-DCCP draft. Next slide, please. We were also part of the first TSV-WG interim meeting in February this year. Just want to highlight here what we presented and discussed during this interim. On the left, you will find the MP Prio option, which I already introduced, which gives us a fine granular path management capability. So we can design with, we can assign up to 4 bits, or we can use up to 4 bits to make different prioritization levels to enable, disable paths, and to give the scheduling engine of the multipath protocol the appropriate input, how to deal with paths. That is, for example, quite useful for ATSS when the Wi-Fi path shall be prioritized over the cellular access. We stabilized, as I also said, the handshaking procedure. We decided for a four-way design, more or less, that resembled the multipath TCP logic, which I think is quite stable. So we adopted this idea. It's not exactly the same as a multipath TCP, but quite similar. So at least this four-way design is taken from there. We presented also some early results of a partial P4 multipath DCCP implementation, which was carried out by Karlsruhe University and has showing the hardware acceleration potential on SmartNICs. I have a dedicated slide to this in the backup. Not sure if you will have time to look into, but as I said, it's the last slide here in this document. So worth to look into. Yeah, and we started to present during the interim what is the relation between 3GPP and IETF if we discuss ATSS related multipath protocols. I will have a dedicated slide on this here as well. Next slide, please.
Can I reclaim it? I'll just stop sharing. Yep, fine. Okay. Wait.
Yes, on this one. Thanks for bringing it back. Yeah, now looking into the new closing procedure we introduced in the latest version of the MP-DCCP. Basically, we defined two new multipath options. One is the fast close, and the other one is just called close. In the fast close, we used to start an abrupt shutdown of the MP-DCCP connection. There's not really a negotiation about that. So if a multipath DCCP peer decides to close a multipath DCCP connection using the MP fast close, it will just send this option over all paths to the peer host. And with sending already shut down the connection on its side. As soon as the MP fast close is received on any of the paths at the peer host will close the multipath DCCP connection as well. So there is not this common procedure of closing a connection, which is known from the DCCP context. For that, we defined a new reset code, a new DCCP reset code with the number 12, and that we also added to the IANA considerations. That this can be adopted then. The MP close that was introduced for a regular DCCP shutdown. So that is more or less following for compatibility reasons the DCCP closing procedure. So we add the MP close to a regular DCCP close request or a DCCP reset packet. The MP close has to be used to shut down all of the paths individually, so it has to be sent on all paths. And first, after all paths are shut down, then the overall multipath DCCP connection will be removed. In general, for both multipath options, we use a key data field that uses some material which was exchanged during the handshake to authenticate subsequent paths. Here we also use it to avoid a misuse of the MP fast close or MP close option, so that man in the middle cannot close a multipath DCCP connection uncoordinated. Next slide, please. Yeah. Yeah, as we are moving forward with our draft, I want to give here an overview what is currently the feature set of the multipass DCCP and what is the maturity of the individual features. So starting on the left, we have finalized the complete handshaking procedure in the draft as well as in the open source prototype. So that is aligned. We use the MP capable feature to negotiate, in general, the multipass capability between two hosts. That is part of the handshaking procedure. And also part of the handshaking procedure is the multipass key option for exchanging the key material I already outlined, which is used to authenticate subsequent flow establishment. Along with that, now I jump a little bit in the table, can we also see in the multipass HMAC that is used in the establishment process of subsequent flows when multipass join is used, which can be found on the right. But staying in the left table, we have the multipass sequence option that carries overall connection sequence number, sorry, which is related to the multipass connection. And last but not least, we have the multipass RTT option, which can carry some timing information that is quite useful in the reordering process we apply on receiver side to compensate latency differences. All in all, the features in the left table we think are complete. Some of them still need some updates for the prototype, but in the draft itself, I think that is stable and ready for being reviewed. On the right, in the partial ready table, I think we also made a lot of progress, but for most of the features, there's still the implementation missing. That is starting with the MP confirm, which we use for reliable exchange of multipass options. It's the multipass join, as I already outlined, to establish subsequent flows. We have a section on a fallback mechanism, so what happens if multipass cannot be negotiated. I think here is some editorial work missing. Then newly added the MP fast close and MP close. Especially for the MP close, it still needs some work in the draft itself. And last but not least, we also have multipass add address, remove address. So in case new IP addresses are identified, which can be used to establish new multipass DCCP subflows, then those options can be used, or in case IP addresses are not available anymore or passes are not available anymore, remove address can be used. And the MP prior, I think I already outlined during this presentation. So draft work is almost completed. And we have now the main focus on the implementation to keep this in line with what we have available in the draft. Next slide, please. Yeah, that is probably interesting for those who are also interested in the 3GPP ATSS functionality. Maybe in one short sentence, the ATSS is part of the 5G system, and it's providing multipass transport from a mobile network operator towards a terminal device, towards a UE. That is where we are very active. That is where we see the multipass DCCP as one solution in that space. And just matching here what we think we already provide with the multipass DCCP, with the draft definition, but also with the published prototype. So if you have a look into the right table, what are the requirements from ATSS? Basically, it needs the multipass transport. It needs non-TCP support. So maybe for those of you who are a little bit more familiar, ATSS is an existing framework. But so far, it only can deal with TCP multipass splitting, because multipass TCP is used for that. So for non-TCP traffic, there is no solution so far, and that is where we look into at the moment. So here for sure, we have the multipass DCCP proposed. We need steering modes. So in the multipass terminology, that are scheduling entities. We need reordering to compensate the path latency differences on receiver side to bring packets in order again. We need path measurement to make good as an input for scheduling decisions, and we need path management to establish or destruct subflows whenever it is required. Matching this on the left with what we provide so far, we think we have now a very, very complete prototype available with the multipath DCCP itself, with a new encapsulation framework, with a lot of scheduling logics, with a lot of reordering logics, multiple congestion controls, CCID 2 and 3, which were already defined for DCCP itself. So those we have adopted, and we're also working on a new CCID 5, which is following the BBR algorithm. Yeah, and last but not least, we also provide path management functionalities. So you see the links here, and they will direct you directly to our GitHub repository where those functions are available. Next slide, please.
Lars is in the queue.
Hi, Marcus. Thanks. Lars, I got actually a question on this slide. So have you started discussing with the Linux NetDev community about upstreaming this?
So good question. At the moment, it's a completely out of tree implementation, which makes it much simpler for us, because for us it's in the foreground to get some first experience before we really make the move to bring this into the mainline.
No, that I totally understand. For MPTCP, the problem was that nobody could really use it because you needed to build custom kernels, and nobody wants to do that. And if you want to run containers with this stuff, you can't, right? So, so it needs to be in the Linux kernel by default if it's supposed to be a building block for like ATSS or something like that, right? Because nobody's going to compile kernels.
Yes, I think we are pretty aware, but we also have to deal with our resources we have available. So that is currently the. So we are, at the moment we just have this Linux reference out of tree implementation available. Nevertheless, I think Karlstadt University they are also working on some user space implementation of this.
Right, that would make a difference. Yeah, but just wanted to check what the status is.
But not sure how mature they are. Maybe that is something for the next IETF where they can present some stats.
Yeah, and I'm not saying that this stops the IETF working on this. Right? I just wanted to know what. Okay, got it. Thank you.
Yeah, thanks a lot, Lars.
We have a question from Michael Tuxen online. Go ahead, Michael.
As far as I know, there are some IPRs involved. So how is the relation between these IPRs and upstreaming this to the Linux kernel and or this open source code? So since you say I can download the open source code, does that mean what's in the IPRs is not in the code?
I think that we declared before working group adoption.
Yes.
So we made it free. Also, the multipath DCCP implementation, the protocol implementation, is part of the Linux kernel network stack. So it's GPL based.
Okay, so no IPRs involved if I use that code.
Yes. Okay. Please do so. That would be great.
Thank you.
Thank you, Michael. Carry on.
Next slide, please.
Next slide.
Yep. So some general updates on where we are now with the multipath DCCP. Here I make again the relation to 3GPP, and I think on that we will also have a side meeting later on after the TSVWT session, where also our 3GPP delegate from Deutsche Telekom will give some insights into how ATSS how it looks like, what are the time constraints from a 3GPP perspective, and so on. So everyone who is interested in that should join the side discussion. Nevertheless, the point I wanted to make is, so multipath DCCP is so far the only solution for non-TCP splitting support, which made it into the technical report after the last SA2 meeting, which has happened in, when was it, February? Yeah, exactly. So for sure, we also expect that the other solutions will come up into this technical report, but so far only multi-pass DCCP there, and we also have some great support from big parties here. I already outlined we have now the full set of functionalities available which are ATSS compatible. I will not repeat all of them. I think I made this clear already. We have a POC agreed with a big terminal vendor who will adopt the multi-pass DCCP into their Android system. So that is where we are currently working on together with this terminal vendor to get some first experience. We also started some exploration of including random linear network coding and combine this with multi-pass DCCP to see the effect, especially when packet loss occurs. Yeah, active draft development is at GitHub with currently 9 contributors. If I look at the time, I think I have to speed up a little bit. So that is the relationship I think we will later on discuss again in the side meeting. So maybe we can skip this for this meeting now.
If you can. There we go.
Very good. Yeah, that is something interesting. So we spontaneously decided to participate in the hackathon. So we just took a free table and started live hacking. So we have a Google Pixel 4 phone now available with multi-pass DCCP integrated. We used it to demonstrate the effect, what happens if the commercial accesses, the Wi-Fi and the 4G access we used in the hackathon room, if one of them fail. So this Google Pixel 4 we connected to a multi-pass DCCP proxy in the internet, and we started a real Skype call between this multi-pass DCCP enabled smartphone and a traditional smartphone without multi-pass DCCP through the MP DCCP proxy. So what happened when one or the currently used access failed, there was an immediate handover into the other access, and there was no interruption in the Skype call. So it works. I have this phone available, and I'm open to present it to anyone who is interested. Yep, coming to the last slide. So we believe with draft version 4, we are feature complete. So we are now in the process of getting reviewers on board, and please feel welcome to join this. That would be really helpful for us. I further outlined that we did a lot of development and a lot of publications around the multi-pass DCCP prototype, including also now the encapsulation framework, which is quite important to enable any type of traffic for multi-pass transport. We are ramping up now POC activities with industry, also to test interoperability, and we will continue result generation and publication together with academia. Our goal is also to keep pace with the 3GPP release 18 timelines. Again, I think that will be something we will later on discuss in the side meeting. The details, when it will happen, you can find here on this slide. So please feel free to join the reviewing queue for multi-pass DCCP. Also to start maybe hacking the prototype would be also great. And with that, I would say, let's go to the question round. Thank you.
So, any questions, please? Thank you ever so much for joining the hackathon. It's always good to see running code, and I think evidence that things work is definitely something that's useful. You'll see the announcement while we're taking questions. This is a TSV-related side meeting across the corridor after the current break, just after the end of this meeting. The room capacity is a little limited because this meeting was called together just to provide some coordination. It's basically just a chance to talk and make sure that people understand the position of different things that are going on. And we're really pleased that we have some participation from 3GPP representatives to help just tell us a little bit more. We have one question. Go ahead.
Yes, checking here. In 3GPP ATSS phase 3 discussion, there was one study topic regarding to use more than 2 parallel passes, like 3 different passes, in order to provide the multi-passings. Well, when you did give the presentation, I tried to look for information regarding that beyond the 2. So can you elaborate on that one? Thank you.
Yep. So if I got your question right, you ask how many paths we support.
Right.
Okay, very good. Yeah, so we are completely agnostic to that. We support as many paths as are available, so we don't have any limitation. So it doesn't matter if there are just 2 paths or 2 access available, or 3 or 4 or 5 or 6.
Okay. Okay, thank you. Oh yeah, by the way, for the 3GPP part, the ATSS multi-pass PCB, they're going to provide some proxy and on some UPF. So for your implementation MPDCCP, are you looking at the similar ones to put some proxy on some sort of UPF in order to provide multi-pass? Thank you.
Yeah, that is maybe something which has to be clarified in 3GPP if there is a certain protocol needed to signal that there is a multipass DCCP proxy. So at the moment, from the multipass DCCP draft itself, there is no support for this, and I think that is also not the idea of the multipass DCCP draft. So that is specifying really the basic protocol and not any proxy functionalities.
Oh, okay. Okay, thank you.
Okay, thank you ever so much. Another question? Oh, David. Question from David.
Marcus, there's some questions in the chat about whether remote participation will be available for the side meeting. Have you made any arrangements?
There is no remote participation support for side meetings. We will make notes and we will distribute some of the materials from that to try and help inform this. This is purely an information distribution meeting. No decisions will be made. Everything that comes out of this will be made available to people. And sorry, but we can't arrange remote participation at that. Martin, thank you.
Just a comment on that. So yeah, so it is IETF policy to not provide the support for remote meetings. That said, if somebody wants to use the VTC client of their choice, that's obviously okay independently. So we can send, if somebody chooses to do that, we just email the list and let people know that's available. Or not, it's up to you to Marcus as the proponent for the meeting.
It's really fun, this. I mean, maybe we need a longer IETF meeting. But yeah, we'll see what we can do. Thomas?
Yeah, I'm not sure what the policies are. If this is TSVWG endorsed, then
it's not TSVWG endorsed, it's TSVWG related.
Okay.
So it's purely information distribution about what is going on and what people think. So it could be in a corridor, but to make it a little bit easier, because we saw several people interested, we booked a side room. So nothing will go in the notes for TSVWG about this, but we will distribute the information to the list. Thanks, Marcus.
Thanks.
So next up in our agenda is discussion of differentiated services. We said we would take Anna first and talk about the considerations for assigning DSCPs. We can advance slides if you're saying next. Not sure who's got slide control.
Is this the latest version of the slide deck?
This is David. I have slide control. Just say next. I'll move them forward.
Okay, thank you. Right, so hi, I'm Anna. I'm here to talk about our draft considerations for assigning diffs of code points. Next. So I'm going to start with some updates. So we published revision 01, and in this revision, we included some clarifications around the different pathologies that can happen to a diff-serve code point as it crosses a path. In particular, we added a new pathology, which is clearing the least significant bits of a DSCP. And since we published that, we also got a load of comments. In particular, thank you very much to Brian Carpenter and Rudiger Geib, who offered some very helpful suggestions. Mostly this is just adding or editing text on how we relate to other RFCs, like 3086 on PHBs, or clarifying some of the text in RFC 2474, and especially what it says about remarking of diff-serve code points at boundaries between domains. We also got some suggestions to talk a bit more about management code points, and also to clarify that the GSMA IR34 standard is not binding and has not necessarily seen a lot of deployment. Oops, sorry. So we're going to make all of these edits. I haven't had a chance to get back to people on the mailing list, but thank you very much. They are very helpful, and I will propose some text, and we will get back to you. Thank you very much. There's something else we want to discuss and we want to include in a future version of the draft. And I'm going to try and paint a picture here on what that is. So next slide, please. So I'm going to start with I have a lot of transitions. I'm going to be saying next a lot. But I'm going to try and show you on this grid, which these are all of the 64 code points arranged in an 8x8 grid. And I'm first going to highlight the ones that have already been assigned. Next. So first off, you have RSU 2474, which specifies the class selector code points. I think this is back in 1998. And these are the code points that keep compatibility with the previous DOS precedence field. Next. Then along come all of the assured forwarding code points, which can also encode drop probability. Next. And then finally, you have 3 more assignments that have been made over the past 20 years. You have one for expedited forwarding. You have one for voice admit. And finally, in 2018, you have one for lower effort. Next, please. On top of all of those assignments, you also have code points. So if you take the binary representation of these code points, those the ones that end in 1-1 are the ones on those 2 columns, and they are reserved for experimental use. Next, please. Right, so this is how the grid looks right now with all of the assignments. And over the years, I've been measuring diff-serve ever since around 2016. And in doing measurements, well, we kind of know what code points are popular in specific types of networks or from specific types of edges. So next, please. So for example, at the web server edge, you see a lot of the AF 11, 21, and 31 code points, and to a lot lesser extent, CS3 and EF. Next, please. Mobile networks. A lot of mobile networks just remark all of the incoming code points to only one value, and that's often AF 11, 12, or 13. Next, please. By examining a large number of packet traces at an internet exchange, we saw a lot of the ICMP traffic does carry a code point CS6 as RFC 2474 states. So that's another one that is used. Next, please. And finally, examining DNS server replies, we see that often they use CS1, that one in particular. All of this is measurement data, and the latest slide deck has an appendix, and all of the highlights of this data and all of the measurements that we conducted are in there. So I thoroughly encourage you to take a look. So next, please. Right, so these are the code points that are used based on measurement data. Unfortunately, the measurement data also highlights a problem. So In our first study that we did, we found a significant number of routers. And what they do is they bleach the 3 most significant bits of a DSCP. We call this pathology TOS precedence bleaching. And it happens on up to 20% of paths. That's what we found in our study. It depends on vantage point, but it's a pathology that we found from every vantage point that we tested. We also validated the data through different methods, validated in a study on edge networks made through RIPE Atlas. And we also found this in the packet trace analysis. So TOS precedence bleaching is extensive. What does it mean? Well, if you clear the top 3 bits of a DSCP, essentially what you end up with a value of the resulting DSCP is between 0 and 7. So for example, AF11 bleaches to DSCP2, EF, which is 46, if you slash off the top 3 bits, it bleaches to 6. Next, please. So essentially, all of the DSCPs on one column will bleach to the lowest value down there of that column. So that is a big problem for assignments. Next, please. Well, why? Well, it's a two-way problem, because if you have all of these popular code points that then get TOS precedence bleached to one small code point, that it means that small code point, be it 2 or 6, then can no longer be used for assignments because it's essentially polluted as it's being used by a lot of other traffic. And also it also has implications for the larger DSCPs, because then if you choose one of them, then for example, if you choose to assign DSCP 9 or 17, then well, if they get TOS precedence bleached, they end up with code point 1, which is used for lower effort. And you really don't want that in an assignment, right? So what do we have in that bottom row? Well, we have 0, which is assign, which is best effort. We have 1, which is assign, lower effort. Next, please. Then we have 2, and as I've said, a lot of traffic aggregates. Well, TOS precedence bleach is down to 2, so that one is not necessarily very usable, at least in the core of the internet. Then we have 3, which is experimental. Next, please. Then we have code point 4, and this one has a different kind of problem. It's more of a historical SSH bug. All SSH, well, not all SSH, but a lot of SSH traffic uses this particular code point, and we've seen this as well in measurements. Next, please. Then we have DSCP5, and we have NQB, which is provisionally allocated to this value. Then we have 6. Next, please. 6 has the exact same problem as 2, but to a lesser extent, because on that column you have EF and AF13, which are quite popular. And then you have 7, which is also left in the experimental. Next, please. Right, so you have a problem with TOS precedence bleaching. So you can either view this in 2 ways. Either TOS precedence bleaching is something that is a given, it happens in the internet, and then assigning one of those code points that is smaller than 7 is a big deal. And then you should consider these smaller code points as aggregates as opposed to assign them for a specific purpose. Or you can consider it's not a problem because TOS bleaching is, after all, a pathology and it shouldn't be happening. And then you have other options. You can just choose, well, you can have a dual allocation like NQB does, and it deals with it that way because it has 1 code point assigned from the edge and 1 code point for the core. And the code point for the core is DSCP5, which is meant to traverse. But what if TOS precedence bleaching was just a pathology? Then you could easily just choose 1 code point to represent the same semantic across both edge and core, right? In any case, whichever way you choose to go about this, you have to think because assigning a small code point kind of risks making code points in the same column unusable. Next slide, please. Right, so underlying all of this, There are essentially 3 cases that I've seen in measurements and from talking to different operators. You either have networks who don't care about diffserv at all, and then they pass code points transparently. And this is a valid use case of this, and we've seen this in measurements. Then you have managed networks, another good use case for diffserv, sorry. So operators police code points, allow only some through, remark the other ones to protect internal nodes in their network, and that's perfectly fine. So in this particular scenario, an operator chooses to support a new code point when it is assigned, and that's fine. So whatever operators do with code points, as long as it's not toss precedence bleaching, then it's fine, because it doesn't affect new assignments of code points. Oh, and then finally, there's the unmanaged networks, or what I call unmanaged networks, that have really weird behavior. I consider toss precedence bleaching to be in this category, for example. But there are also other types of pathologies, like, for example, bleaching the other 3 bits of the TSCP, and that happens, but only in some very few weird networks. And you can have inconsistent remarking. Anyway, problem networks. And basically, we'd like to propose some text about this. We'd like to get input from the working group on what to say about them. Next slide, please. So yeah, what do we say about them will go in the next version of the draft. I guess at the moment, our draft is informational. We don't know if we could maybe make recommendations for future assignments. I mean, I'm going to include the table and the implications that I've just talked about in the new version, alongside with the text that other people proposed. And maybe it's also worthwhile talking to operators to understand a little bit more about how things are used. But yeah, that concludes my presentation. What I have is a lot of appendix slides with lots of data, so please be sure to check those out. Thank you.
Thank you, Anna. Do we have any questions? We have Martin at the mic. That'll be good.
Martin Duke, Google. First of all, I'd like, this is my first opportunity to thank you in person for doing this draft. I'm learning a ton just listening to all this, and that grid you showed just really makes it super clear that we're burning the last generally useful code point, which is pause for some reflection on this. Yeah, like I would encourage you to take this to maybe ops area next time. That might be a good step in terms of the operator survey. You may not reach the people who are still bleaching, because those are generally less informed, less connected people, but nevertheless, that is a good entrance point into this, into that community. But yeah, mainly thanks. So your intent is still to have this be an informational draft, and your potential, if I'm not mistaken, and you're proposing potentially additional draft that was that, like, what's the new draft supposed to be?
The next revision of this draft.
Oh, okay.
Sorry.
Okay, right. Okay, maybe step in as chair here. So the current work item is informational.
Yes.
And I guess this draft will be revised as informational.
Sure.
And it is informational until we get to the point where we start clarifying the way that these 20-year-old RFCs are being updated based on the current practice. So I hadn't realized this when we started it, but maybe Brian's Carpenter's post recently on the mailing list was actually quite deep, quite useful. Maybe after 20 years, we should reflect on what the best practice is as we deal with the last few code point registrations. We should kind of get this right. So I think Anna's line of this document is informational is quite correct. If we think ahead, if we decide to do anything more, then this document maybe either has to have a pair, which is not information, but maybe BCP or PS or whatever it is. And that would be a change for the whole diffserv architecture, which is currently all recommended. Well, okay, so the thing is, it would be good to get discussion on the data that Anna's had and to decide on the way forward. I don't think this blocks the NQB work, by the way, because I think we can, for NQB, we can find the right answer now, and then we really don't have very many code points left, so we have to decide what we're doing in future. So I think these things could work in parallel. It'd be interesting to see how that pans out.
Yeah, I mean, I would just looking, I mean, having been aware of this for 5 minutes now, I would be tempted to try to engage with the operator community and see if we can handle this bleaching situation, which I think would be great if we could fix it. But secondly, like, I mean, we've got a lot of experimental code points, and maybe like deprecating half of them would be wise. So we have a 3-bit code point that is available. It just be off the top of my head. I mean, obviously it's not a fully considered opinion.
I think we need to consider.
Yeah.
What Anna marked as experimental was actually local use, and experimental local use of DSCPs is incredibly important.
Yeah.
And we also have managed use of DSCPs and networks that just pass DSCPs without doing a lot of changes to them, and those which do changes which are historically based, which are kind of maybe harmful. So there's maybe different categories. So this is going to be a thing that's useful to explore. I suspect other people in the queue are going to talk about this.
Yes.
And yes, I think we should take it to Ops area. I think that was a wonderful suggestion. So as a co-contributor to Anna's work, I think a presentation in Ops area would be so wonderful.
All right, thank you.
Thanks.
And after all that, we have now Rudiger, who's also been active on the mailing list. And Rudiger, please speak to the mic.
Yeah, I hope you can hear me.
We can hear you. Please go ahead.
Great. Yeah, I'm Rudiger Geib. I'm configuring bleaching at the edge routers of Deutsche Telekom. And long-term DiffServ participant. I appreciate work on an update of the existing drafts, because I think, and I contributed a lot of my operational experience. And what I'd like to have or like to see in future is something which allows for default transport in the backbone, default saying just default, nothing else, but service differentiation in the access, and that should be also standardized sharing of resources. And what I'm aware of is you can either optimize for throughput, or you optimize for performance, which is low jitter and low delay. I don't want to say it's that or this option, just should be fair and not discriminate against others. So there are no pipes. It's just a default behavior in the backbone and a standardized behavior on the access, how resources are shared. And I can tell you that many people who request quality of service concepts from me nowadays come and ask for exactly that. Thank you.
Sorry, was there a question?
No question. It was.
I guess the question. I guess we can include Rudiger's comments in that part of the draft.
Yes, of
yeah.
course. Sorry.
If the result of your draft is to recommend an update of the DiffServ specifications, I really appreciate that. Thanks.
Okay. That's useful input as well. Thank you, Rudiger. Let's continue this on the mailing list. Jonathan Morton.
Just like to express support for some kind of BCP or DiffServ RFC updates to try to discourage the use of bleaching in the network in some effective way. So yes, we can continue this offline.
Yes, it's in line as well with what we're thinking.
Okay, right. So the answer is please revise the draft. Please consider a presentation to Ops area to try and tell them what we have found. And also let's probe on what we mean by recommendations, but do these three activities separately. Revise the draft, think of a presentation to Ops area at the next IETF, and also think about whether the recommendations for the use of diffserv code points could be something we discuss on list and come to some consensus about. These might have very different timeframes, but thank you ever so much for the talk.
Yes, I'll start the process on the mailing list for the 1 and the 3rd things you just mentioned.
Thank you, Anna. Wonderful. Oh, they are. They appeared. Excellent. We have a question from Bob Briscoe and Sabia. So, Bob, please go ahead.
I was just going to suggest as well as up to area the IEG, which is an informal operator group that opens on Sunday morning before the IETF. I'll put chat.
Bob, you completely broke up.
IEPG?
Can anyone channel Bob, or can Bob type that into the chat?
Yeah.
Excellent. That would help.
I think he said what I was also going to say, that you should also look at the IEPG meeting on Sundays, which is a sort of operator hangout thing that's adjacent to the IETF. So Warren Kumari is sort of involved with that, if you know him, or talk to me afterwards. I'm not involved, but I can point you at people.
Would love an introduction.
Definitely. So there's a bunch of operators that meet like on Sundays and chat about things.
This Sunday.
This would every IETF Sunday they meet.
Oh,
so
right.
thanks.
Yeah. So the comment was consider also IEPG, where you can have the same talk with a very different focus because it's operators who are probably really engaged with this. Yeah. So IEPG as well.
Okay.
And was that Bob's comment? Yes. As far as we know. Right. Please go ahead.
Yeah, this is Sabir. 2 quick questions. One is you mentioned that there may be an operator survey. Will that happen? And the second one is that when the recommendation will come, will the recommendation will come to TSVG or somewhere else?
Easy questions to answer. Thanks ever so much for asking. We can launch an operator survey. We would have to do that, of course, with the ops area because it's an operator survey. And I think operator surveys have worked quite well in that area. So we might try that. I will speak to Warren. Yes, the recommendation will come from this working group, but clearly this is something that is a fairly substantial change to the way the internet routers work and the way we operate them. So other groups would have to be involved if we change the recommendations, which is kind of why I'm leaning towards separating the 2 discussions into here's the information on what we have and how we register things, and here's any new considerations that we have out of it as a standards track document, which we'll have to go around the IETF with.
Okay.
This is a working group to discuss this.
That's very good. So I think I heard you also mention that that recommendation possibly will imply that to look at diffserv architecture. Am I correct?
It looks like it might, because the current diffserv architecture is all recommended. It was put in place about 20 years ago to make something work when nothing worked. Now we have things working, we might be able to change that a little bit. However, if it's working well, we might want to make small changes.
Thanks.
Thank you, Sabir. Final questions? Great. Keep going. Jake, please talk.
Yeah, I want to echo Martin's. This was really good. I felt like I learned a ton in 10 minutes, and I would encourage you to also take this to MapRG as a measurement presentation there. I think you would, not only the operator community, but I suspect many others in the IETF community and the associated research communities would benefit from understanding these observations. Thank you.
Thank you.
Thanks, Jake.
Like I'm going to have a very busy next IETF.
Thank you, Anna. I think you've had enough invitations for the moment for doing more work. Please do some more work and come back. And with that, I do encourage us to use the mailing list, and we will move forward with the next draft, which is one which I think Greg will present remotely. Greg, are you online?
Just 1, 2.
Excellent. please speak to your slides.
All right. Thank you. You can go on to the next slide. This is a brief update for the NQB draft. Obviously, some discussion around code point assignments will continue on the mailing list. But I here just wanted to cover the edits that were made in the draft recently. And I did do a presentation at the interim a short time ago. So not a lot of time has passed since then, but one update to the draft has been made, this draft 10. And I can go on to the next slide. I did send a list of the edits to the mailing list. This is verbatim what I sent. Next slide has a little bit better breakdown of what the changes really amount to. This version here is kind of going section by section in the document, but if you go on to the next slide, really summarizes what the changes were. First one is the section in the draft that talks about what types of senders are compatible with the NQB marking and would be recommended to mark their traffic as NQB. In particular, it talks about sparse flows or sparse applications that are sending at a relatively low rate. And for those who attended the last IETF, as well as the interim, note that that's been a point of discussion for a couple of rounds to try to get that language right. And so hopefully we got it right this time, but I encourage folks to take a look at that. And if there are further comments or suggestions on refining that language, I certainly would appreciate hearing those. The second item is some more discussion around the rationale for the choice of the code point 45. And this was sparked by some comments I received off list that suggested that that a little bit more background and rationale would be helpful for explaining that. The third item, additional implication of EDCA manipulation. This was a comment on the mailing list that pointed that the draft suggests that one approach to making legacy Wi-Fi networks look a lot more like they're supporting the NQB PHB. In other words, make them support at least some of the requirements of the PHB can be achieved by changing the EDCA parameters that are used for the video access category. And one thing the draft didn't state directly, and was commented on the mailing list, is that, well, by doing that, you give up a priority queue. So you turn a priority queue into a queue that has the same priority as best effort. And so now there's a discussion of that or statement on about that in the draft. And then fourth bullet, the IANA section. So reformatted that to align with expectations for the instructions to IANA. And also, per a comment at the interim, gave unique names for the two code points, 45 and 5. The names I've chosen are NQB Edge and NQB Core, although it's kind of an open question to the working group. Are those the right names? I think some of the discussion about task precedence bleaching and other network effects that remark code points. We might consider whether those are the right names or not, but I think again some broader discussion on that will hopefully shake that out. And then finally, some editorial nits I cleaned up along the way. And that's it for the changes so far. At this point, go to the next slide. Really been looking for other comments, other review comments before starting working group last call. Obviously, the recent comments about code point assignment, I think we need to conclude those on the mailing list before taking this to working group last fall. Looks like Gory, have your hand up?
Gori Ferhas talking from the floor so I can stretch and get some exercise. Yeah, thanks, Greg. I think the whole DSCP thing can be dealt with. And I like the change of two registry names. Registering them with different names is probably right. I only wonder if we should think about adding some text about why we are doing this. And also to perhaps clarify what the aggregate or low numbered, in this case 5, DSCP point actually means when we have other assignments with other DSCPs in the same column of Anna's table. So these seem like things which we should talk about. They don't affect NQB, but they may affect whether we choose should, must, may, and what words we write. So I think that might be a useful input from the floor as an individual.
Right. All right, thanks. Yeah, the should remark and should not use the value 45 across interconnects. I think that's the areas where I agree that we need consensus on those. And it does kind of get back to what is the end-to-end philosophy for DiffServ going forward. It seems like there's some view that DiffServ is by intention AS specific or domain specific, and then obviously other views that it was ideally intended for end-to-end use. So yeah.
And we have David in the queue as well. David?
There for the history, DiffServ was trying to be both, was trying to allow individual networks to configure the services that they wanted to configure and provide opportunity for end-to-end services. The end-to-end has not worked out all that well. See Anna's wonderful slides for the gory details.
Any other questions? Okay, maybe David, do you think we're near a working group last call? Because it seems like the framework's closed and all we have to do is pin down some new text around the use of these DiffServ code points. Is there anything else you think needs to be considered for a working group last call to start?
I think that's about it. We should also have a real close look at exactly what we want to call the 2 new code points, but I think that's about right, and I think we're close.
Comment from Jonathan Morton.
This is actually from Jabber. Sebastian Möller asks, what is the time frame for the 45 assignment? If NQB becomes popular and supported ubiquitously, keeping 45 seems not needed, as this is only to fudge NQB into existing or future legacy Wi-Fi deployment.
What's the time frame? I think there are applications that today would like to be marking their traffic with NQB code point. There currently isn't one that's formally assigned, and so application developers have had to use alternate or been suggested to use alternate code points that that could also be classified into the same or aggregated into the same PHP and NQB PHP. So I think that there's a demand for a code point sooner rather than later.
Maybe part of the question here is how long do we need the allocation for? I wondered how good your crystal ball was. Do you think 45 will work across the internet core in 5 years' time and we don't need the 5 assignment? Or do you think we need the 5 assignment forever and we don't need 45 because all the Wi-Fi equipment will be updated within 5 years? Do we have any clue about where things are going?
How long a version of no would you like to hear, Gory?
Well, I just thought it would be worth asking the question. I thought the answer might be no, we don't have a great crystal ball, and this has always been a problem in the IETF. We don't know what's going to be adopted by whom. We just encourage adoption, and then maybe we have to figure out the text appropriately in the way we can consider the outcomes. Jonathan, do you have more follow-up?
Sebastian says that you have conveyed the core of his question correctly.
And I would comment that as the draft is currently written, the 45 assignment is long-term because that's what's recommended to endpoints to signal use of this PHP.
Yeah, good point.
Thank you. Let's have a short, focused set of questions, Greg, after you've done any revised work, and work with the chairs on those questions, and let's then try and get them cleared so we can get to that working group last call.
Sounds good.
We'll do our best to help. Everyone else, please join in. Thank you. That closes the DSCP part of our schedule. We're a little later than the agenda, but I think we're still on time for all presentations. So the next presentation will be by Tom Herbert. I took the decision to have a slightly longer slot for Tom so that he could have a full half hour, just because this is an interesting and useful background, particularly for UDP options, but also for anyone who's in the transport area and wants to know about what is currently going on with implementation of internet checksums in real equipment. So go ahead, Tom. Tell us, please.
Thank you. So my name is Tom Herbert, as Gory mentioned, and I'm going to give a little bit of a presentation on how we're implementing the internet checksum. So as Gory said, this is kind of a relevant topic. It comes up a lot. UDP encapsulation, there's a lot of discussion on that, actually any encapsulation. But we're also seeing questions being raised in UDP options, and just yesterday, Fred Templin's talk on IP parcels, the topic also came up. So the topic is relevant because the internet checksum, as we know, it's quite pervasive. It's in all major transport protocols, UDP, TCP. It's also in IPv4 and the IPv4 header checksum. Kind of the go-to validation check. We like it because it's really simple, easy to compute. That's really just an addition. It's well known that it's not the strongest verification checks, but the thing that makes it relevant, particularly to the implementation, is it can be very costly if we don't optimize it properly. Computing a sum over some field of bytes, if we have to do that, for instance, in the CPU on a TCP packet, a large TCP packet, that could easily overwhelm the CPU because of the per byte cost of processing. So there's been a lot of work on the implementation side to really optimize this. And I'll touch on some of that today. But I think the relevance with protocols, especially a new one, is when a new protocol is being developed, we do have to consider the implementation effects, particularly something that is potentially costly, like the internet checksum. Next slide, please. So a little bit primer on the internet checksums. So they are 16-bit values. Usually they're put into a 2-byte field in a packet, and that will be used as kind of the validation code. The algorithm is a ones complement 2-byte sum. And typically this just starts from a start offset in the packet to the end. So we're going to basically sum up all the 2-byte words in the packet from some beginning point, usually to the end. And that gives us an answer, and that answer is kind of the check. The sender and the receiver effectively both perform the same algorithm. The sender actually sets the sum such that it sums to a known value. In the case of the internet checksum, it would be all ones, FFFF. And the receiver performs the same algorithm, so it adds up the same bytes. And all it has to do is match the answer to the expected answer. And if it matches, then we assume the packet is correct. So as I mentioned, it's using TCP, UDP, the IPv4 header checksum, GRE checksum. UDP options will have a checksum also, and probably used in several other transport and possibly even some layer 2 protocols or layer 3 protocols. Next slide, please. So the algorithm, the specific operation, it's one's complement addition. And the idea of one's complement addition is we add 2 binary numbers of some word size. It's normal addition. If a carry is generated, though, that carry is added back into the result to get the final answer. So in this example, we're adding 210 as a byte and plus 106. That does generate a carry in basically the higher order bits. So higher order bits generate the carry, and all we do is add the carry back in. So the sum in this case is 3D or 61. Next slide, please. So one of the nice things about the internet checksum, it has a lot of very nice arithmetic properties that we can work with and do some optimizations. And you can contrast this, for instance, to some of the stronger checksums or verification codes like CRC32, which don't have these properties and actually makes them harder to compute or harder to use. So one of the first properties that is well known and it's actually used in internet checksums today, all ones is mathematically equivalent to 0 in one's complement addition. So for instance, if we have a word and we add the all F's version of that, that actually equals the starting word. So it's an identity. So there are effectively 2 zeros in checksum or one's complement addition. It's also commutative and associative. So we can add 2 words, we can switch the order and get the same result. And then we can group sums together in different combinations and get the same result. So given a set of words that we're summing through one's complement addition, we can sum them up in any order. We can reverse them. We can group them together. So there's a lot of options there. And that is going to actually be quite useful in some of the kind of sub-algorithms that we have when we're manipulating checksum. We can also define a checksum subtraction, which is basically the not operation. So if we have a word and we add, do a one's complement add of the not of that, so we flip all the bits, so 0 becomes 1, 1 becomes 0. If we add those together, then the sum is always all ones. And again, that's equivalent to a checksum 0 value. So sum's basically 0. The other one is that checksums of a larger word size can be folded to a smaller word size with basically an equivalency. So we can take a 32-bit checksum value, for instance, and we can perform an operation and make that a 16-bit checksum value, which is equivalent checksum going from 32 to 16 bits. It doesn't work the other way, but we can go from larger word sizes to smaller word sizes. And I'll have an example a little bit later on what the procedure for that is. Next slide. So the internet checksum, as I mentioned, it's a one's complement sum. And what we do to set it is there's a start offset in the packet. So in the case of TCP, for instance, this would be the first byte of the TCP header. There's an end offset. Typically, that's the end of the packet. And we sum all the 2-byte words from the first byte, the start offset, to the end offset. If it's an odd number of bytes, then we simply virtually add on a 0, logically add on a 0 to the end. In some protocols, for instance, TCP and UDP, there is a pseudo header. So the pseudo header is also added in. The idea of the pseudo header is to protect bytes and fields outside of the checksum coverage area. So for instance, a pseudo header would include the IP addresses and the length in the case of TCP checksum. So the pseudo header is created, that's obviously standard. We do the ones complement sum over the pseudo header. We add that to the ones complement sum over that coverage area from the start to the end offset. That gives us the full ones complement sum. And then we basically take the knot of that, and that becomes the result. And I should have mentioned that before this operation commences, if the checksum field is within the area that we're checksumming, usually we'll set that to 0 for the purposes of computation. And then once we have the result, which is again is summing over all of the bytes that are covered, we take the knot of that and we set that value into the checksum field. And then the result of that is when the receiver performs the same algorithm. So we'll do the sum from the start offset to the end offset, and away add in the pseudo header, the result will, the correct result would be all ones, FFFF in the case of the internet, 16-bit internet checksum. Next slide, please. So as I mentioned, that's the purpose of validation. So same algorithm, there's a pseudo header. If there's no pseudo header, like in the case of GRE checksum, then effectively you just add in a 0, which means it's a no-op. And again, if the result is all ones, we consider the checksum valid. If it's not, then it's considered to be a corrupted packet. Next slide. So as I mentioned, the internet checksum, it's computationally expensive. We do have to basically touch every byte, every word of a packet in the case of something like a TCP or UDP checksum. So there is a lot of motivation to optimize this. And over the years, there has been a lot of work to do just that. We can actually divide this into basically 2 areas. So we have some checksums that cover small amounts of data. The best example of that is the IP header checksum. Typically, this is 20 bytes, maybe up to 40 bytes. It's a very small amount of data. So the direction we've gone on that is to have very specialized CPU instructions to handle that case, basically a ones complement addition instruction. The other side of this is large packets. This is like payloads. So this, for instance, is the typical case of TCP and UDP, where we're calculating the checksum over the full payload, which could be thousands of bytes. In that case, it really warrants checksum offload. This is when we basically have the hardware actually perform the checksum on behalf of the host. And all NIC vendors, for instance, today support some variant of checksum offload. It's heavily motivated, obviously, by TCP, where the checksum wasn't or is never optional, but also UDP. So what they've done is they have optimized the NICs in a couple of ways. We'll get into that in a moment. But the upshot of this is for TCP and UDP checksums, from a host perspective, the NICs actually do all of the work. And basically, we completely save the CPU. It's already baked in. These have been around for a very long time. So generally, this sort of checksum computation is not considered to be a problem in terms of performance at this point. Next slide, please. So if we look at the kind of the naive method to write a checksum algorithm in pseudocode. So we want to do a 16-bit sum. And as I mentioned, if the first thing we want to do is check if the length is odd. If it is, we have to add that extra byte. So in this case, we're just literally tacking on the byte and increasing the length to make it even. And then we go over a loop. And the loop is going over each 2 bytes. And it performs a sum of each of those 2 bytes, each word. So the sum, the 4th line there, we're just adding every 2 bytes and having a running sum. And each time we do the add, we have to check the carry. if the carry is set, which is what that check is, if sum 16 is greater than all ones, then we add the carry back in and proceed to the next 2 words. So it's, again, a running ones complement sum, where we're basically performing a normal addition of 2 bytes and then adding in the checksum if the carry, or adding in the carry if it was set. Next slide, please. So the first optimization.
Tom, we could take Torless. He has a question.
Yeah. So just, is there any good data? You know what the biggest reasons are for checksum errors, and you know what their probabilities are? Or just kind of, you know, the use case always escaped me from the analysis.
Yes, there has been a lot of work on that. I think it's probably out of the scope of this presentation. But we do know, for instance, that checksum is susceptible to certain combinations. It will detect all 1-byte errors, but it's possible that it can miss, or 1-bit errors. It's possible it can miss 2-bit errors because they can cancel out each other. So it's stronger than parity, much weaker than CRC, but it will provide some validation.
I was just wondering, kind of the most simple answer for this is what actually happens, and it protects against it. That kind of the motivational question.
Are you asking, is it memory copies or DMA failures or something?
Exactly, something like that, right? What's the biggest reason?
Oh, what's the source of the errors?
Yeah, that it actually does protect against, right? So the biggest reason that, because, you know,
I would say
we very often had these discussions about when can I leave away the checksum. Remember, Gori, right? So when we did these tunnel things and UDP without checksum, so there was the ongoing debate. But me coming mostly from the network side, I never looked into the end-to-end, which is what the expensive part is. So I was just curious.
Thank you.
Yes, I would suspect it would be in the network if there is an error. Modern computers obviously have a bunch of redundancy checks and have ECC and memory, so it's much less likely. Network corruption is probably more likely. It's still not super likely. As I mentioned, we do know the internet checksum is fairly weak. If we need strong integrity checks for security purposes, for instance, then we do have to use much stronger things, much stronger calculations. So one question that often comes up is, why isn't the Ethernet CRC sufficient? The main difference is the internet checksum is end-to-end. So Ethernet CRC does a much stronger protection. That's always in hardware. Internet checksum, however, is much weaker. There's also another value to it. In the case of something like UDP options, the checksum actually can be used to differentiate between standard uses of a byte space and non-standard use cases. So a non-standard use case may still be valid, but it might not be what we expect, and the checksum would actually protect us there.
A question from Richard in the queue.
Yeah, not a question, but an observation. So from my experience with our customers, we have checksum errors typically in the order of perhaps once a year across the entirety of our customer base. And that typically happens with fairly old network gear, which has not ECC protected memory. And when basically the packet is in flight and you have unprotected or undetected multi-bit errors, which then show up in higher layers of the protocol, where you do have CRCs that will flag a bad transport in TCP, for example.
Okay. Thanks, Richard. Tom, you have about 10 minutes left.
Okay. So one of the optimizations, the first one is we can actually sum over larger words, as I mentioned. So we can do a 32-bit addition, and we can translate that into 16 bits. Next slide, please. So in this case, we could have the same loop, but now the boundary for the loop, instead of being length divided by 2, becomes length divided by 4. So basically, if we sum 32-bit words instead of 16, we have the number of additions. So hence, that's a very nice performance improvement. Next slide. So this is forwarding the checksum to 16 bits. It's pretty straightforward. Basically, just add, if we start with 32-bit value, add the high order 16 bits, low order 16 bits, do one's complement sum, and the result is basically the folded value. And again, this falls out from the arithmetic properties of the checksum. Next slide, please. On modern CPUs, as I mentioned, there are specific instructions to do this, to optimize the one's complement addition. In x86, for instance, there's an add with carry. The add instruction itself sets a carry bit in a control register on x86. And then the specialized instruction, add with carry, performs an add, but then it does that check of the carry and adds the result back in. So this is used extensively in networking stack, for instance, when we want to implement the checksum over the IPv4 header. This basically is resolved to a few adds with carries. Next slide, please. So I'll briefly touch on this. This is actually code to do checks on the IPv4 header. The first section is actually doing 8 bytes at a time. So in order to checksum over 20, or do checksum calculation over 20 bytes, we do an 8-byte add, an 8-byte add, and then a 4-byte add, and all those are one's complement add. And at the end, we add in the carry bit when it was generated. So that's what those first four instructions are doing. And then the rest are the operation. We're basically folding 16 bits down to 32 bits, and then 32 bits down to 16 bits. Next slide, please. So I'll touch on this briefly. One of the common operations in dealing with checksum is if a packet header is updated, for instance, in NAT, the IP addresses are updated. We do not want to recompute the full IP checksum. We don't want to recompute the full TCP checksum. What we can actually do is figure out what the delta is, meaning if we add a certain value into the checksum field, that would basically offset the change we made elsewhere in the packet. So very, very common thing to do. And it's also very highly performant because we can even pre-compute in some cases this addition. So updating the checksum for something like NAT may come down to one single add with carry operation, one complement addition, and then set the field. So this, again, the arithmetic properties of checksum make this highly efficient in order to do things like this. Next slide, please. So checksum offload, as I mentioned, is very useful to get performance when we're offloading or when we're processing TCP and UDP checksum. As I mentioned, all NICs have this. There's actually two methods. I'm only going to touch on the more common method, or at least the preferred method, which is what we call protocol agnostic offload. So this is a case where the NIC, which is network interface controller that's performing the checksum calculations on behalf of the host, does not need to know what the particular protocols in the packet are. It can do a checksum calculation both on send and receive for arbitrary protocols, works for encapsulated checksums, and we can use these techniques to validate multiple checksums per packet. The alternative is more of a legacy mode, which older devices did, and some of the original checksum offloads did this. They only understand certain protocols and can do verifications on those protocols. However, outside of that, for instance, introducing new encapsulation, we found that it basically don't work. So there's a strong preference in the community to use protocol agnostic offloads. And in the case of checksum, that is really important because of encapsulations and other uses of checksum. Next slide, please. So the transmit checksum offload, basically this is following the same procedure as a host, except we're going to tell the NIC or the device how to do it. So we send the start offset, the end offset in a transmit descriptor. Usually the end offset is the end of the packet, so that's kind of implicit. And we give the device where to put the checksum. The one thing the host has to do is it will kind of prime the checksum field. So for instance, if the pseudo header is involved, like in case of TCP, the host will compute the ones complement sum of the pseudo header and knot it, and then set it into the checksum field. So when the device gets this packet via a transmit descriptor, it performs the calculation, and all it does is start from the starting offset to the end of the packet, perform the ones complement sum, and set the result in the checksum field. It doesn't have to worry about the pseudo header because that's already been taken care of by the host. Next slide, please. So I'll skip this for a day. I just wanted to touch on there is a way to do multiple checksums per packet. In particular, network devices, they only have the capability to offload one checksum per packet. However, we also want to take advantage of that to offload multiple of them, like in the case of UDP encapsulation, where the UDP checksum may be sent and the TCP checksum may also be set. We want to offload both of those. There is a way to do this called local checksum offload without requiring the device to actually compute a checksum twice. Next slide. So receive checksum offload is also similar. So we want a protocol agnostic way to do that. What we do is we just have the device calculate the ones complement sum over the whole packet, and it will return that sum to the host. And then the host stack can take that sum and it can manipulate it such that it can derive the checksum over any bytes of the packet. Basically, the way it does that is, as it goes through the packet, it will do a ones complement subtraction of the small checksum. So for instance, if we want to derive, in this case, the IC sum, which is the checksum covering, or actually UDP checksum, if we have the full checksum value from the beginning to the end of the packet, what we do is we subtract out the ones complement sum of the IPv6 header. And in this case, there is a surplus area. We subtract that out. What's left is precisely the sum over the UDP and UDP payload. And then the host can use that to calculate the checksum. So this did require the host to do a couple of checksum calculations, but they're on the small portions of the packet, not the big portion. Next slide, please. So similarly to transmit, we do want to be able to support offloading of 3 checksums. This kind of naturally works on the receive side because of the algorithm I just described. So we don't need any special support from the device. All we need really is that full checksum, what we call checksum complete. Next slide. So I will touch on these briefly. Both the receive and the transmit, one of the things we want to do is what's called GSO, TSO, and LRO. This is where we want to use larger packets from the stack's perspective. And then when we're sending, we want to break those packets into smaller MTU size packets for transmit. And similarly on receive, we want to collect together some number of packets on a flow, maybe make a super packet and give that to the stack. We get a lot of advantages from this if we are able to process larger packets versus smaller packets. So it reduces the per packet overhead if we can coalesce packets like this. We also have to consider the checksum, though, when we're both sending and receiving. So I don't have time to cover this today, but there has been a lot of work in this area. And in fact, GSO and TSO and LRO, they become quite critical again for performance. So we do want to maintain these. And this is another area where the checksum becomes relevant because we still want to maintain the properties of the checksum in terms of performance. And I believe that's all I have for today. Any questions?
Thank you. We'll take questions. We had a few during. Jonathan Morton. Go ahead, Jonathan.
More of an observation here. The checksum delta technique is very useful for updating fields in the IP header, for example, that commonly get changed en route, such as the ECN field. There can be bugs in these implementations, and these result in certain packets that have been changed en route having incorrect checksums while the rest are correct. So it's a useful technique. You just have to make sure you get it right. Otherwise, you get problems that might sometimes be hard to notice. Because an incorrect received checksum looks like a dropped packet, which has the same effect on congestion control as a CE mark, for example.
Yes.
Can I put myself in the queue and just ask a question, Tom? Does the set of changes which Joe Touch put into UDP options since the last IETF meeting, where we placed the checksum in a particular place, does that make it easier to do the offload? How do you feel about that new placement?
The stack will basically, when it creates a packet, it'll know where the checksum is. So it's not super critical for it to be in a fixed location. However, the device also may have constraints. So for instance, it's very likely that a device, when it wants to offload a checksum, the start offset may have to be, and both of the offsets may need to be within the header of the packet. So all these devices really assume that the checksum we're offloading in the field are in the header because they may only have, for instance, a 1 byte offset field. Real estate in the transmit descriptor is very costly, so we can only get a few bytes for this. So they may use a single byte. Typically, we assume that the checksum is at a 2 byte alignment. So 256 of 256 values, we can double that, which means the checksum could be anywhere up to 500 and I guess 10 bytes into the packet. So having it at a fixed location isn't as relevant as having it make sure it's aligned to an offset of 2 bytes and try to keep it within the header of the packet so that we can put it in, we can fit it into the device. Obviously, software stacks, it's not so relevant. There may be some instances, particularly on some older systems, where they don't really like to do unaligned operations. So it's very basically like I think all the currently defined protocols, the checksum start should always be 2 byte aligned to avoid any issues with unaligned operations.
Yeah, and I think that alignment is what's in the current draft.
Okay, so yeah, I noticed it was 1 byte aligned. So I'd also point out there's a little bit of a misnomer that I see come up, particularly this is in the context of UDP encapsulation and in the context of UDP options. When someone sets the mix of checksum optional, that is not necessarily saving cycles or saving performance. And in fact, in some cases, it can be worse. And the reason for this is, if you consider something like UDP encapsulation, where RFC, I think 6935 and 6936, basically allow checksum 0 even in IPv6, where IPv6 basically states that checksum is always required. In certain circumstances, particularly from a host point of view, if someone sets the checksum to 0, thinking that that's going to save cycles, we may still have to compute the checksum because there's an embedded TCP packet and we're receiving this on, say, a host in a virtual network that has a number of VMs. So we still have to offload that TCP checksum. So we're not really saving much there because we have to go through all the algorithms. And as I pointed out, we're still going to get the full checksum from the device anyway. But the problem is, in some of the legacy checksum algorithms that I described, if we set a checksum to 0 and we still have to offload that inner TCP checksum, this receiver may in fact have to go through the whole checksum calculation on the host, which is really where performance drops significantly. So I think the checksum we've absorbed, at least on the host and the NIC stack, there's very little value to disabling the checksum performance-wise from a host perspective. The only reason I think that you would disable it is if the device, like routers, which was the motivation for disabling the checksum in IPv6, if they're communicating and they're terminating UDP, they may not have any hardware to support checksum offload. But disabling the checksum is hardly ever an advantage from a host point of view. It's more likely to be a disadvantage performance-wise.
And the routers also presumably had the offset problem that they couldn't see deep into the packet payload when they were doing re-encapsulation.
Right, and yeah, so there's obviously there's a lot of discussion on this, but I do want to stress this fact, and I said it before. We've absorbed it. The cost of the UDP, the TCP checksum, that's not a current problem we have. The current problem we have is when new protocols are introduced, how do we continue to leverage those and not accidentally introduce some sort of protocol combination where we're computing checksums on the host, and basically the performance is such that the new protocol may not even be viable. So this is where really the implementation becomes critical. We have to consider the implementation in these new protocols.
Thank you. We'll move to Joel's presentation now.
Thank you.
Thank you, Tom, for that. Oh, and I'm going to be Joe, so just... So, Gori Fairhurst proxying, as Joe touched on the UDP options update. There's just 5 slides. The first one talks about core updates between version 13 and version 15. The first one being the new option area structure, which is why we allocated most of the time in TSVWG to the overview by Tom on what the OCS is doing, which is the checksum that's applied in UDP options over the options area, where it's placed and how it's aligned. This is now in the draft. It's been in for a little while, being revised, so the text should now be good. Please look at this if that concerns you. Joe also integrated the unsafe kinds, primarily to do with fragmentation, and the fragmentation text was updated. Request response was now required as an option. In other words, if you're implementing UDP options, we expect that function to be part of the implementation you provide. Next slide. There are a few other updates. Obviously, NITs, we got quite a lot of feedback via the working group. And in the working group feedback, people noticed little inconsistencies, numbers that didn't form a complete series, numbers that were missing, and a few places where we made clarifications about the format. One of the things we did change in the more recent versions is to decide when the OCS field was optional, the thing that Tom was just talking about, whether we should have an optional mode to OCS. The conclusion come by Joe, reflecting the current revision, is that the UDP options checksum, the OCS, is only zeroable when the UDP checksum is 0. This means that it doesn't affect NAT traversal, and it means by default, if you supply UDP checksum, then you must have an OCS checksum. I think the other updates are fairly minor. If you've been following this, you'll have seen that these were introduced in version 15, and Joe's just pushed version 16, which corrects this and some other things. So next slide. This is 15 to 16, specific limits on options. Corrected the table of contents. Corrected a lot of the terminology. As you can see, Joe thinks this is now reaching maturity. Next slide. And there are a few pending updates, meaning that Joe is going to produce a new version of the document. I'll happily take questions from anyone who wants to ask questions and see if I can answer them. Otherwise, we'll push them to Joe. Does anybody have any questions on this draft?
Tom, go ahead.
So I asked this on the mailing list. What is the state of implementation? Do we have any information on that?
I think the question is really directed to Joe and the working group in general. With implementation experience of the latest version, I have not heard anything discussed on the mailing list. Please bring it there. The general concept of UDP options was that an earlier version of this was implemented. Tom Jones will speak on DPLP MTUD, and he did part of that implementation work. It wasn't pushed to kernel. It wasn't reflecting the latest version of this draft, but it demonstrates perhaps that the thing might well be implementable. As in other areas, we'd love an activity to implement this. We'd love a hackathon activity to take and make something out of this. Implementation experiences will be welcome. Does that answer, Tom, or do you want to follow up?
I mean, at this point, it would be really good to have that.
Excellent. Clashing Toms, that's good. Is that the last slide? Okay, I'm going to move to the working group chair position, because I'll sit down. I'll just announce that when we complete the revision of UDP options that's coming, we expect the document to be stable. And at this point, I've invited some people to review this on behalf of TSVWG. Tommy Pauley and Colin Perkins have agreed to look through the specification and see if they can see anything from a full read-through. As this is our first stage of review, this is a new transport protocol. We've done this same procedure for DCCP and SCTP, so we're going to get some independent reviews. Based on their output, we expect a further revision and then a working group last call. Please provide comments. And finally, Tom. Tom's going to talk about DPLP MTUD.
Can I have the next slide, please? This is just our names. So we have the DPLP MTUD UDP options document. It just provides additional text on top of UDP options to explain how to integrate the requirements to implement DPLP MTUD, so the formats and a bit about how to send packets. It's a really short document. It'd be great if more people could read it. Since the last revision, we've aligned this with Joe's spec. A lot of this alignment has just been minor updates in terminology and what things are called. And so we changed probe token to nonce value because that's what the language Joe went to. We clarified that we can't send the two kinds of options more than once in each datagram. We've rewritten some of the text on probing with data to make it easier to follow. It's a small change. It's a really small document. We don't have a ton to say right now. And if we go to the next slide, I think the most important question is there. We think we're finished. I know we're metered by UDP options proper, but we think we're done. We'd love to get some more feedback from the working group. I actually think this document could probably be almost wrapped up, pending just minor changes from Joe in terminology and language and UDP options. So what does the working group think? Are we done? Can we be done?
Anybody got any questions? Anyone want to comment on this one? Go ahead, Chris.
Yes, Mike Hurd. I read the document. I didn't post any comments to the mailing list because I didn't have any. It looks really good. The one question I'd have for you, Tom and Gory, would you envisage that the DPL the DPLP MTUD procedure could be implemented as a shim on top of the UDP options rather than being integrated into it? I ask that because that makes a difference in what we want to specify in the base spec for an upper layer interface. I think that's something that hasn't really gotten sufficient attention and scrutiny. Thank you.
I am not really sure what the question is. I think you mean, so if we're using the UDP options to implement DPLP MTUD, then it's not really a shim. I think the service offered to the upper layer is reporting the discovered value, turning on and off DPL PMQD, and maybe tweaking some of the parameters. There's an SCTP implementation of DPL PMQD, which is experimental, which has sort of 5 parameters to it. So it's a really small service set. I don't really know how you would shim this in. It's not really a core part of UDP options because it is protocol action rather than just the wire format, which is most of UDP options. So yeah, I'm a bit, maybe you could clarify.
Of time, perhaps I'd better think it up and put the question in writing to you.
Cool.
I guess the chair action is this document will be declared finished if nobody comes and says that more work is needed. So please review, please check it. And if I hear nothing, then we will ask the co-chairs to start a working group last call on this, although we will probably keep that in synchronization with the UDP options-based spec. It's 12 noon and we're at the end of the meeting. Unless anybody has a final statement, I will say goodbye to you. I will start saying goodbye now. Thank you ever so much for attending TSVWG. We look forward to participation on the mailing list. There is a side meeting occurring at 12:30 if you wish to join, and look forward to seeing you in the email list, perhaps in Philadelphia. Bye-bye.
Happy lunchtime, everyone.